Welcome to Physics 2, Lab 3. So our lab is about understanding the impact of magnets on the things around them, where we have a system, magnet, and our magnetometer, and our surroundings, which is everything else. So the magnetometer can measure the magnetic field of a bar magnet, such as this one, so that we can find the dipole moment of the magnetic field. Our results do find that this is our dipole moment, but how did we find this? Well, we have our equations. This is our magnetic field equation in a general sense, but this can be used at any point of anywhere, but most of the time we're going to have it perpendicular or on axis. So we can just use this equation right here, where this is our little dipole moment, and this is a magnetic constant. Now we also know that we have these two equations that are going to be very important in the next slide, which is going to help us find our magnetic field and our equation, our dipole moment. So this is our little data here. So this is our off-axis field, and over here, most importantly, we take down the distances whenever we have approximately a certain amount of our magnetic field, where this is approximately 20, this is approximately 70, but of course we take down all these actual numbers. And then this takes that in as an equation, essentially, with all of this, and that will pop out a slope, which is equal to this little n value right here, and our height, which will be our k value over here. Once we have all that, we find that our mu value, or our dipole moment, is 2.105. Now let's put that into our in our code. We have a function which will take in two different vectors, essentially, and it will take in the dipole moment vector and the distance vector. It will take that distance vector and normalize it and find the magnitude of it, and then we will use it in our magnetic field equation so that we can return that magnetic field vector at a distance. And then over here, we want to find different observation points and observation axes. So we take a couple that are parallel to, and then 4 that are perpendicular to. And then we just simply have that axis is equal to one of these observations. We'll put that into our little function that we made so that we can find the axis vector. And then we represent it with an arrow and print out what that value is, and then we'll do it for all of these observation axes. And then we essentially have the same thing, but over here, this is going to be our off axes, so it's neither perpendicular nor parallel, which is why we need the generalized magnetic field over here. So we put it in where we want to find it with a more special observation point. So here are our results. We see our representation of our electromagnetic field, which should make sense if you look at a general magnetic field. And here are all of the resulting magnetic field vectors. If we hadn't oriented to compensate for magnetic north, we would have to compensate in our code and in our calculations by having an extra vector which would be added into our magnetic field. if we were to stick two identical magnets together, the dipole moment would probably be found to be twice as strong, as they would be identical and therefore most likely have the exact same dipole moment. And what could be possibilities for errors or similarities and differences? For one thing, we could have just had an issue with the magnetometer. The magnetometer could have been wrong, or the code could have been wrong, or the magnet was defective in some way.